This is a lecture about what I call here motor control, which is really the physical dynamics, mechanical dynamics of these kind of actuators of arms and their control. How to make them do the movement we want them to do. The term motor control is used in the human movement community, interestingly. It's not so commonly used in engineering, really. I like that term. So in human motor control, that's about how to actually bring about the movement with your muscles, right? How to physically do it. And in the robot, you have to say the same thing. So we have to understand the mechanical dynamics, the kinetics. We have to understand actually the actuators. I'll not talk much about that. And that's very different in humans and in robots, right? In humans, it's muscles, and robots, it's traditionally kind of electrical motor, and then principles of control. They're very good sources. I mentioned both of these books earlier for kinematics, and they're actually very good. The second book, Lynch, is really quite easy, well written in terms of pedagogy. The first is very mathematical. The second is very accessible. It's available online, like a preprint is available online. So you might have found it in the meantime, it's very good. The first is actually available in the first edition, also online. Okay, so what is, so first half, I'll talk about mechanics. Now, this is something that some of you have learned in high school, perhaps, and others, I don't know. Physicists, of course, have learned that. We have a few physicists here from biomedical physics. Everyone else, I'm not sure where you actually learned that. Newton's law. You learned that in high school? Yeah? Okay, you didn't have differential equations, so, or did you? Maybe you did. Yeah, okay. So you're familiar with Newton's law in this form, probably. So that x2 dot is the acceleration if x is some kind of positional variable, the mass, m. So mass times acceleration equals force. It's actually a bit unclear what exactly force means. And sometimes it's defined as that thing on the right-hand side of that equation. And it's important that x is an inertial frame, a non-accelerated frame that goes at constant velocity in some absolute sense, right? And there was a long debate about that. So we're, for instance, strictly speaking, not in an inertial frame here. Anybody knows why we're not in an inertial frame? Any idea? Here, this room, is that an inertial frame, strictly speaking? Yeah, do you think it is? Anyone? Approximately it is, but it's not really, because we're on the surface of the Earth, which is rotating, and the rotation creates some acceleration, right? Because the velocity vector has to change all the time. So we have acting on us apparent forces that are, because we're not in an inertial frame, one of those is the Coriolis force. And some of you might know there is this pendulum, for instance, in the Deutsche Museum in Munich. You have one of those pendula that where the plane of oscillation rotates to the Coriolis force that comes from that rotation. And of course, it can be neglected. It's very small. It can be neglected for many purposes. So it's interesting, there is an absolute frame to that. You could be somewhere in the universe and then just find out in which frame you are. We're also rotating around the galaxy. Our sun is a very small effect for us. So there are a couple of reasons why we're not in this, strictly speaking, right? In practice, we can neglect that. So the non-inertial frames have these other forces. Now you will see in robot arms that occurs always, because if we're looking at one joint, it is attached to the kinematic chain, and that joint will be very often not in an inertial frame. Now, because I'm moving around my shoulder, and my wrist is actually now in a frame where the velocity vector changes direction, right? And that's non-inertial. It's a acceleration due to rotation, and that creates these forces we originally called about centripetal forces, sometimes also called centrifugal forces. So just a question which way around you look at it, and Coriolis forces. If you don't really know these, there were wonderful demos on YouTube, physics tutorials that have very nice illustrations of these kind of things. Some of them are really fun. Just goes too far to look at that. So you could already maybe guess that using Newton's equation for a robot arm is going to be complicated, because they're not really inertial frames as you go along. So that's quite nightmarish to do it. There's another reason why it's not ideal to do that because there are these constraints, right, that we talked about in kinematics 2 weeks ago. So for instance, if you have these two segments and they're connected by revolute joints, so one axis of rotation, then what we said is that one of those segments, like the upper arm, the lower arm, will have only 1 degree of freedom left. So rather than writing down Newton's equation for the 6 degrees of freedom of the segment, we are supposed to only write one equation for that whole thing, right? It's only 1 degree of freedom. And so how to do that? How do you reduce that? That's complicated. Now, so that's the question of how many degrees of freedom you have. Now, these are holonomic degrees of freedom. That is, mathematically, you could write down the original equation in the original space. I just wrote the translational part, and there would be a rotational part as well. And then you would have a constraint equation that allows you to eliminate some of those variables, but it's going to be analytically quite complex. So fortunately, a much easier approach was invented in the 19th century. That was, I don't know, many people contributed it. Now it's called sometimes the Lagrangian approach. And that's the idea that you can use variables that are called generalized, that are variables that characterize the kinematic state of the system, but they don't have to be these particular physical variables that describe the particle, a rigid body's state in an inertial frame. Maybe we could close the window. I think this gets a little annoying. Yes, please.
Consider the unlimited degrees of freedom. For example, the robot arm is moving and there's for some reason a force at the joint that it doesn't support. It might take damage of the.
I didn't really understand that. So the arm is moving and then what? It hits something?
No, it doesn't hit. For example, if I move my arm like this and this joint is locked. And if I rapidly stop, it might still experience some force in this direction.
Yes, so there are two aspects here. One is the one that you might be getting at, which we call interaction torques. I'll refer to that a little later. So that will be, for instance, if I have this, I actuate this joint and accelerate around this joint, there is some torque felt because of the non-inertial frame in this joint. And for instance, if I don't do anything, then my wrist will be flopping around due to the, we call those interaction torque. That is, torques brought onto the elbow will exert a torque on the wrist as well, because it puts the wrist into a non-inertial frame. So these apparent forces arise. Those are a real control problem that one has to deal with. We humans actively compensate for those. So for instance, if you move your elbow like this, and this is stiff, then you can actually observe that the muscles that stabilize the wrist are actively engaged, in fact, in a predictive way. They're even engaged before the force, the acceleration is sensed, to compensate for that. That's maybe what you meant. The other thing is, of course, is if you have any of these revolute joints, they restrict the degrees of freedom by exerting forces orthogonal to them, right? So for instance, if you have a revolute joint and you, like this was a robot arm, right? And I apply some torque in this direction, and it's just one revolute joint. I don't have any, not a human arm. Then that's going to be resisted by the mechanics, right? By the anchoring of the joint, and that's going to make forces. And if the arm is a little bit elastic, it could deform the arm, and that is not treated usually. That would be, ultimately the arm will break, let's say, or would have some vibrations and so on. So these things are not treated at the level of kinetics and kinematics. These would be problems of the mechanical construction, understanding what kind of stresses occur in the metal and so on. Maybe, I'm not sure that's what you were referring to. And this is interesting, mechanical engineers who have to think about how, heavy the arm has to be, what kind of steel to use, would it resist the kind of forces that arise due to the imposing the constraints. And will be to see what kind of shear forces, for instance, arise in the arm and make sure they can sustain that. But the roboticist at the level of control just assumes it's built well enough so it's not going to break, and then it just deals with the degrees of freedom that are actually there. Okay, good. So this Lagrangian approach, let's check who actually has heard that before? Lagrangian mechanics. One person nods. Online, nobody raises a hand. It's not so common. That's, of course, what you learn in physics, like theoretical physics 1, the mechanics. That's what you learn. You don't really use Newton at all. So, it's usually half a semester to understand that. So I just give you a little flavor of that, like in 10 minutes, right? And so in the Lagrangian approach, what that allows you is it allows you to write down the equation of motion of, for instance, kinematic chain, just using these funny variables. These generalized coordinates mean you have some variables. We would typically take joint angles that just uniquely describe the configuration, but they don't have to have the physical meaning of these original, positional. Newtonian approach, ultimately, it's a question about momenta and position. So velocity and position, roughly. You don't need to use these physical variables. You can just use any variables. That's why they call those generalized coordinates. So for instance, the joint angles are sufficient to uniquely describe the configuration of the arm. And now you have to write down the equation of motion for the joint angles. Quite complex to derive that from the Newtonian equation, you can imagine, right? That would be a non-trivial task. But the Lagrangian principle allows you to directly write down the equation of motion. And that ultimately is connected to deep stuff in mechanics. It has to do with something called action. I'm not going to really explain that here. It also has deep connections to quantum mechanics, actually. There is a third approach, which is actually very much used in quantum mechanics, called the Hamiltonian approach, which we don't use in robotics, which has other advantages. And that's actually the one that's primarily used in modern physics. So the Lagrangian is just a function. This function, where's my cursor? Just a moment here. Here. This function that is a function of the generalized coordinates. In general, it's a function of the coordinates at any moment in time and their rate of change, q dot. For instance, joint angles and joint angle rate of change. And it's simply defined as the kinetic energy of the kinematic chain minus the potential energy. So you could think of it as, as you know, there's energy conservation. So the universe we're looking at here in mechanics, there are only these two forms of energy, kinetic and potential. Potential is really gravity here, right? And you know that their sum is constant, and I'll have to later look at friction. So the sum is constant, and so the difference, so if you increase kinetic energy, then potential goes down and vice versa. And then you can think of, this sort of keeps track of how much conversion you're making, right? When you move an arm, you're making conversion all the time between these two sorts of energies. This is still without any actuators, right? This is the conservative closed system, so there's no energy in, no energy out. No, it's just the arm with no friction, flopping around in gravity. So the integral over time of that is called the action, and it's one of the physical insights that the realized trajectories by any system like that are the trajectories where that integral is minimal. So the change is sort of a variational, this uses variation calculus, which you don't have to understand fully. This is something like the generalization of the infinitesimal element, dq is on what the infinitesimal element of any variable, and this is of a whole function, so the minimal element of that function. So the variation of that integral of the action is 0. That's a prerequisite for the action being minimal. And that is a very, you can actually derive all mechanics from that postulate. And that has its equivalent in quantum mechanics. Some of you might know the Feynman integral is actually exactly that. So when you have that, you can derive the equation of motion. This is called the Euler-Lagrange equation. This method of computing the minimum goes back to Euler. And you have to understand. So you can treat that variation just like a derivative. So you can put it here under the integral. So you take the derivative with respect to delta, to q, and then have variation of q as a function, again, as a function of time. and then you take the derivative with respect to this q dot and take the variation of q dot. And so that has to be 0, and then you have to know that the derivation of a derivative is the same as you can exchange that you can exchange the variation and the derivative. So you can take the variation of q first and then apply the derivative. And when you do that, then you have, you can take this dq out of the equation, and then you can apply partial integration. For those of you who know that, you can try to reproduce that at home. And what you then find is that the first term, the dq goes outside, and the first term is here, and the second term by partial integration is then the derivative dt on the left, and then the d by dq dot on the right. And in partial integration, you also get this term here, the one you originally had at the upper and lower boundary, but because at the boundaries you fix the time course, it's the initial condition and the final condition, and so that's 0, and therefore you get that this here is the integral that's 0, and because it's true for all variations, the term in front of that term has to be 0 for this to be true, and that's the equation. So this here is the Lagrange equation, the other Lagrange equation. So this equation as such, you couldn't immediately maybe make sense of it, but that is essentially the equivalent of the Newton equation in Lagrange calculus. Now, in practice, we're using a variation of this approach, because in practice, we're not having conservative systems. We may have friction. Some of the models have friction, but we also insert these torques right into the system. And these torques are essentially deviation from 0. There's an insertion here of external forces, and the nature of these forces depends not on the variables that you choose. So if we have joint angles, then we can identify what is on the right-hand side. It will be a torque that's on the right-hand side. Now, this is again vector-wise. So if I write down the components, this depends on all 3 components. If you have, well, as many as you have along the kinematic change, and this too, right? So it's as many equations as you have generalized coordinates. So if you have a joint robot arm with 7 joints, let's say, you have 7 such equations. And they are coupled. It will be a mixture. So let's look at a few examples to get a sense for that. Again, you don't have to understand the equations, just to see a little bit what the principle is. So for instance, the simplest textbook example, I have a pendulum in 3D. So a rope here, a mass, which is treated as a point mass. So gravitational force on that is proportional to the mass and the gravitation constant. And it has 2 degrees of freedom, right? You can rotate in this plane, so this way or that way, or you could take an azimuth angle and then the angle within any of these planes, right? So the theta is one, and then projection onto the plane would be the other joint angle. So one is theta, the other is phi, 2 generalized coordinates. See, to write down the equation of motion of that from just the equation of motion of it would be easy to write down for the free point mass, but it's much more, with the constraint of being on that rope, we consider massless, is much more complicated, right? And so the Lagrangian approach is really powerful. It's kind of straightforward to write down the kinematic energy that just depends on the velocity of this point mass. And then if you figure out with this constraint, the velocity is essentially caused by velocity along this and along that. You figure out the trigonometric equations, and you have to take the inertial moment around, when this whole configuration, when the mass is all here, and this is the length of the rotating idea. So something you can compute, that's the inertial moment of that. So then you get this and that as the 2 contributions to kinematic energy. Somebody who knows these equations can write this down like in 10 minutes. And the potential energy just depends on this angle, right? If you're rotating in the plane, doesn't really change the elevation. So just as you elevate this this rope a little bit, then the gravitational energy will change. Essentially, this height you determines it. That's the cosine of that angle. So the Lagrangian is this here. You have to understand this is the mathematical definition of these 2 joint angles for 3D position of this point mass. And then you just go put it into this machinery, compute all these derivatives, and then you find that is the equation of motion. So there are two equations, two variables. They have the acceleration terms here. In front of them is a matrix. We call that the inertial matrix. And then there is a term that contains joint angles and their derivative in some complicated form. That's actually here all just centrifugal terms. And then there is a vector that only depends on the joint angle. That's the gravitational term. For the theta phi variable, there is no gravitational term because that is a variable that keeps the elevation of the ball in a plane, and only for the other one is there a gravitational term, and that is zero if there's no actuation in that. So this is a fairly complex equation. Now that, well, it's not super complex, but not totally trivial to write down. And this Lagrangian approach really makes it easy to derive that kind of equation. Closer to home, this would be the approach to a planar two-link robot. That's, I think, in the textbook that I just recommended. And you can very analogous, you can imagine you have to just compute the kinetic energy of these things and of the segments. And you know, have to take the variables take care of the constraints. So you just can say, if I have that segment, what is the kinetic energy? It has two components, the translational one, so the center of mass of each of these segments along x and y. You know, velocity squared times the mass, that's kinetic energy of, again, there is some reason why you can just consider that a point mass. You can just consider the center of gravity having that mass, and that mass moving around. It's the kinetic energy of translation, and the kinetic energy of rotation. You can define relative to the way you define the joint, around that. You can define compute the inertial moment for that. That's the inertial moment, which has a couple of terms, and then just the rotational velocity squared, right? That gives you the inertial moment, inertial moment, yes, times velocity squared gives you the angular, the kinetic energy. That's the rotational kinetic energy, and then the same thing for the other segment where the effective angle is the sum of these two joint angles. There's a general way of writing that. And again, you just take the derivative, apply the Lagrange formula, and you get this kind of equation. This contains a lot of abbreviations. The C2 is cosine of theta 2, and S1 is sine of theta 1, so almost the same terms that show up. And you find the structure is, again, this general form that the accelerations are multiplied with something. That's the inertial matrix. And then there is terms that mix velocity, always linear in velocity, and then they have additional velocity and potentially position terms. There's none here. Those are, again, the centrifugal and Coriolis forces. And then there are, in this case, zero to the right, or the generalized form, if I have actuators on this that insert torque into these joints, then you will have the torque showing up here on the right. In fact, that is the general form of the mechanical dynamics, kinetics of kinematic chains. They have this general form. The acceleration multiplied with a matrix that depends on theta, that's the inertial term. Then a velocity term is a vector, each of those, multiplied with a matrix that depends on both velocity or potentially can depend on both. That's the centrifugal and Coriolis force. That's where the interaction torques come from. And then the gravitational, which generally doesn't depend on n dot, actually. I should have cut that out. That is the gravitational term. And then what is remaining on the right are any torques inserted into the joints. So some of those terms are intuitive. You remember maybe from high school that the inertial moment is larger if you distribute the mass more broadly. So for instance, if I rotate around this, then my inertial moment is larger than if I rotate like that, right? And so I need actually I need less torque around some joint here to accelerate if I have the arms in than if I have the arms out, right? And, yeah. And the other term, I think perhaps about this is very analogous. So if you have the same velocities of your hand far out, there is more energy in that. So this is a famous example of these ice dancers, right? If they pull in the armor out, then they energy conservation makes that they rotate faster, and that is ultimately the balance between these two terms here. Gravitation is also very intuitive if something is high versus something is low, and that what violates the model is the active torque. So that mostly roboticists just know this equation, and then for every robot they look up the concrete terms in here. When we model, we actually model human motion, then we build models like that of human skeletal arrangement that we look at. This much about dynamics. So very, very briefly, there's of course a whole chapter in that book just to give you the flavor. It's 19th century mathematics, but no. Now, control. That's again another course, a whole course to look at. Or I should actually sometimes ask questions. Any question about this part? Yeah, so it's just a high level view of all of it. Good. So control. Yes.
They will have to follow without physical background.
Yeah, I'm pretty sure it is. Yeah. So there's this is robotics is a very interdisciplinary field, and there are a lot of people who do aspects of robotics who don't really understand that either. They just take this is like the axiom, and they take these things and take them for granted. So it's important for those who do control. It's sometimes also important for planning, as I'll show out. So I'll show later. There is a way of integrating planning with control. I'll come to that. Good. So control. Well, this is a very general scheme. This is from a textbook of control. This idea that when you think of control again, is bringing about physically the thing that you desire, right? So there's an idea that you have some desire, you have some representation of what you want that system to do. So what the output of that system is supposed to be like, right? We sometimes call it the desired trajectory, desired, whatever it is, and the little d in the equations. And then you have a machinery where you compute from that stuff so that the process ultimately returns that, and you have a loop where you have some kind of sensory information about what actually was generated as output, and you correct what you sent into the system. And this chain here is sometimes cut up into different pieces depending on how detailed you're analyzing this. So ultimately the process is whatever that is. The robot arm would be ultimately that mechanical device. And you may have a particular way of influencing that process. With the robot arm, it's of course the motors mounted on the joints, and that's what would be the actuator. Like a chemical plant, it would be perhaps some valves that you can act on and so on. And you would have a controller, which is the thing how you can, tell your actuator what to do. For instance, on a robot arm, I'll get to that in a moment, might be something electrical, some current you send to the motor. It's different from the physical action of the motor, right? And so then the comparison is essentially your control algorithm, how you're going to combine the desired output and the sensory input to send something down there. And that's where the notion of error comes. That is, you're thinking that under some circumstances you would be able to represent here whether you're doing exactly what you want to do. And then you don't have to have any control correction of your command. So if it does exactly what you would do, then the error would be 0. So the way these control people describe that mathematically is that they have these 3 notions. They have some representation of that other thing. They don't always really, depends on how, if you have separate variables for this and that. So it's all lumped into one big state vector, X. You have the output, which is the thing that your sensors react to, which could be some transformation of your state vector. And you have your control signal, so the thing that you compute and then send to your actuator. So they always use the letter U for that. Now, there are more complex things. I think I have that in some other slides. Yeah, that you're sometimes distinguishing between the actual output and then the estimated output, because your sensors may also have their own properties and they are not able to correctly estimate the exact output, they just have some estimate of it. Often the difference between those two is just some assumed noise, there's a measurement error. It can also be some bias that you're systematically misestimating something. And so what you're seeking when you're designing a control system is you're seeking some function, how y depends on the current output and on the desired output. And when you have that function, then analyze what would happen and to treat all disturbances or the things that could lead to variation other than the variation you induce by your controlling as stochastic, as ideally having zero mean, if your model is good enough, zero mean, and just having some variance. There's, of course, much large field how to actually do that. So for the robot, more concretely, the actuators are typically just the motors. There are also robots that have more complex things like with transmissions or Getriebe, which we're not looking at here, but we're just thinking about actuators. And so the device that controls those is something electrical, amplifier kind of system. And actually in many of those systems, there is another feedback loop here. So you could think of that as another minor thing of that whole loop, where you're actually correcting the action of the amplifier by measuring something mechanical about your motor, not yet about your arm. That is actually, these are the servo motors. And the fact that we have this very good loop makes that we can give electrical signals to the motors that already have some mechanical meaning. And that's an achievement. If you just take an electrical motor as such, that wouldn't be the case. Then the same voltage you send to the motor would make quite different effects on depending on how much resistance there is, for instance. But this is really makes robotic control much easier these days. Other than that, it's just the same diagram. And this is this particular thing that you do have a control loop where you're also sensing the electrical current in the motor, and that current reflects how much it took up your command and actually generated the physical force or torque that you wanted to do it. And by doing that well, you can make that the signal that you send, even though it's an electrical signal, you can say it corresponds to a desired torque. It's not going to be exactly the same, but it's a very good approximation. So very often you can neglect the difference between the desired torque of the motor and the actual torque, and you can say what kind of electrical current I have to set to get the torque right. And that makes control much easier of these arms. So that's why electric motors are so attractive for robots, right? This is a whole business, and there's still some people doing that using pneumatic robots, which have mechanically some attractive properties. Pneumatic with pressured air. But for instance, they have some elasticity properties that are nice. But there is much less clear how the signal you send, the correspondence with the mechanical effect of it. So this is very convenient. It also has the downside, there is no compliance built in. It will do rather brutal stuff sometimes. And we have much more compliance as humans. But for classical control, this is very nice. So I don't want to explain that exactly. Okay, so so to make this more concrete, what you have is that you have as input desired behavior. The desired behavior is usually a trajectory of the robot. Let's say in the simplest case would be really a trajectory of all the degrees of freedom of the robot, all the joint angles that you want to have. So you have that is a given, right? That comes from your planning. You know what movement you want to make from kinematics, right? And now you have to set up a control law that, given that trajectory, tells you what commands to give to that robot arm. And as I just said, the motors are such that you can think of that command as a torque that you send a desired torque to the motors, and to a good degree, they will realize that desired torque. And any deviation that then leads to the motion not being exactly as you want is then compensated for by the control law that we're now going to think about. Now I have there's a whole literature, and actually there's a lot of theoretical work on this. And the state of the art now is that this is very mature, and the textbook stuff, I'll mention some of that is here and works very well. And the current algorithms used in robot arms are actually proprietary. These companies have used control schemes and optimized those and so on. It's no longer really something that is publicly researched. There are a few exceptions. The most famous exception is space robotics, space arms. I mentioned that, I think, in my introductory lecture, where you have the special constraint that you have a robot arm on the shuttle. There was this robot arm, right? And there you have to be really sure that you don't create a lot of unnecessarily torques, because the arm is screwed to the space station, not to the Earth, and the space station will start to wobble if you do wild stuff. So you want to do like really minimal intervention to really transmit as little torque as possible to the arm. And then there are sophisticated ways of how to do that. And so on. There was actually a real German contribution from the DLR in Munich to one of those robot arms, which was essentially designed by them. Now, there's also a lot of interest now for human-like movement and torque control and so on. So making them more elastic and things like that. I'll just mention that very briefly at the end. Okay. So now let's just look at what then control means. So control will mean that you will arrange that the degree of freedom, let's say this is a joint angle and you are initially here and you want the joint angle to go to a new value. And what you need to do is that it comes about in time, that you go to that new value. You will transform this desired state into an error, which is the deviation from your current state to that desired state. And you want that to be small, so ultimately be 0, right? And if you keep changing this, then there's a whole trajectory. So ideally, your error would be always 0, and then your arm would exactly track that desired trajectory. And in practice, it will tend to lag a little bit behind, and it might have a little bit of an oscillatory component, like it has a little overshoot, and there's some damping until this overshoot is sort of taken away. And you imagine that limits how quickly, how variable in time your desired trajectory can be. You can't have a very rapid trajectory if you're lagging behind too much, right? So it's just the position of that control determines how rapid the movements are that you can impose, that you can actually follow. So that's characterized in control theory, theoretical terms, by the two eigenvalues of the two components of the eigenvalues. So for those of you who know that kind of math, you know that you can linearize the control matrix and you end up with you can diagonalize that matrix, and the eigenvalues are complex, and the imaginary part essentially reflects the frequency of these oscillations around the controlled state, and the real part is essentially a measure of the damping of this. So if you're very much a very negative real part, then you're very short settling time. It's very rapid damping. It goes, very settles very quickly. If you have positive eigenvalue, you're unstable. Remember that from our use of dynamics for planning, for motion planning, right? It's analogous. Then so you have an attractor, a fixed point attractor here on the left, and a unstable fixed point on the right. And the imaginary part, something we neglected so far, which is tell us if it goes to the attractor just relaxing or it goes in overshooting, oscillating. And sometimes you might want to have critical damping that is just as it relaxes, it also just makes one cycle. So it's sort of the same time scale for these two. So engineers just look at where the eigenvalues, like they talk about these as roots because they're computed from some equation where the roots lie, and like these crosses here would be roots, the eigenvalues, and you can read off if this is a good control or not. They want this to be somewhat on the left, maybe not too stiff, because that could create a lot of force, very high forces that you have to impose, but not unstable, of course. Here's an example. This is the example actually where we introduce here damping, and damping is not in the Lagrange equations, right? They are for exact equations. So you have to use a generalized form of a Lagrange equation where there's a damping term. Damping violates, of course, energy consumption, just like the torque insertion, right? Generating torque actively is a violation of energy. The motor uses energy, and damping is a problem. So some of these equations use damping as well. And then I don't need to go into that. So I encourage you to look up this example. It's in the book. This example of a single joint, single actuated element. So let's say screwed to here. There's a revolute joint somewhere, and that's connected to the table. It's just like there's this inverted pendulum kind of display. You sometimes see that where through some control you have to have a single degree of freedom that maybe is upright because gravity would attack the center of gravity or center of mass. So they have a damping term here. This is the gravitational force, that's acceleration, very simple. And so you want to control that. So its equation of motion is this here. So it's the same as essentially, you can even look at it as a Newtonian equation. Not quite, but good, very intuitive, right? The acceleration, this is the gravitational term, and this is the torque. This would be damping. And so remember, we're thinking in robotics that the actuator gets as a command a torque signal. So we've taken care of the motor, that we can say whatever we give to the motor electrically, it actually amounts to a torque. So we just want to determine what kind of torque should we insert into that system. And so this is the classical PID controller. I think all of you might have heard about it, where you're essentially saying, I put in nothing if I'm already at the desired state. So my desired theta, here desired theta is exactly what I'm determining, what I actually have as a theta, and then my error is signal and I'm not sending anything. And the deviation from that is this error, and that is a proportion term. So this has this matrix in general. Here's actually just a number. And so that will be, the sign will be chosen for this to be stable. So when you're a little bit too larger theta, you insert a torque that goes in the opposing direction. You have to figure out the sign. And there's so this will be the proportional term. The D differential term is that if your velocity is not zero, so it's a little positive velocity, let's say, you want to have zero velocity. So you're going to insert something that reduces the velocity as the opposite sign. So that's going to be your contribution. And then the integral term is very tricky. That's the dangerous one. The PD controller is actually the safe thing that you can use all the time. I'll say a little bit about the integral controller. The integral controller says that if persistently your theta is off, then this should be still theta error. Your theta is off, then I'm going to counteract that to make it persistently go away. We'll come back to that. So here are examples of this acting. So for instance, your PID controller will make your error really nicely zero under some circumstances, and whether it overshoots or not depends on the parameters it chose for the controller. These various parameters. You see an example. If I want to control this, let's say I give as a target configuration like this horizontal configuration, you see that in that configuration there is a constant term, the gravitational term, that is going to pull this down, and therefore in that configuration it's not going to be enough to just send some torque that corrects things, right? So only, let's say these two terms, these correction terms, they will go to zero when the error is zero, right? So if there is a constant force on this, the gravitational force, they don't counteract that force. Only once the force has induced an error, then they will correct that. So you find that if you only use these two terms, it will never really rest up here. It will have some position like that, because there will be an error, and that error makes a torque, and that torque compensates for gravity, because gravity is acting on that. And that's not really desired. So what you want to do is you want to accumulate that error here. See, this is how this controller ends up at a non-zero value. And here you're accumulating this error, and then you're giving more and more torque to that, so that now ultimately until it is actually has reduced that to zero. So then you're going to have that kind of perfect behavior. This is a very dangerous term. You can imagine if you are not reaching the goal because you're hitting a human or as a table that you didn't plan for, then it will ramp up its torque, up to the upper limit. So it will use as much force as it has to achieve the goal. So it's very dangerous if you have a systematic error that isn't really cannot really be overcome, and this will try to overcome it. And so the integral term is to be used with caution. In fact, you could think this was a mistake. I should have thought about this problem and inserted, computed the torque and have some extra term just for compensating for gravity. That would be actually the correct, better solution. And so this is sort of the generalization of that one that compensates for dynamics. So let's say if you here no feedback, if I just, you could say I could just control this without feedback, then I don't have these funny problems, but just computing what kind of torque I need to achieve the state. And this could be done by having a model of the dynamics. So here M tilde is supposed to be the model of the actual physical thing, like the equation I wrote down. And similar, H is the model here of the Coriolis and centrifugal forces. And then if I compute the desired torque to have this shape, then just add that here on that equation. That will be this sort of thing. And I insert here the desired trajectory. And if these models are good, so this M tilde is about like the M, the H is about, like what is here, and I sort of say approximately this term is like that term because my theta is close enough to the desired theta. And similar, this term is like that term with theta close enough. Then the equation you get is that from this, you could put this on the left-hand side, and then you have the theta desired 2 dot is equal to the theta dot. In other words, your theta will behave like your desired theta. So just putting in this torque, your system will behave like your desired trajectory. And that's by essentially copying the equation of motion and canceling all the terms except for the term that just says the system is the same. You can see it's just not very stable because if the accelerations are approximately the same, but still the difference could accumulate over time, and that could be a problem. And that's illustrated here. If there's some systematic mistake in your model, there's no reason why the two actually stay close. They can actually go far from each other. And that's the drawback of having that. But on the other hand, in a first approximation, it does get the right behavior out of the model. Yeah? By you having computed what kind of torque would be needed or would be observed if I would actually do the design. As you can think of this, if this is your model, you just put in the desired here and see what kind of torque would be arising if you do that. That's the computed torque. And you say, okay, that's the torque I'm going to insert. And then it's going to do exactly that. Well, it's only going to do that. But theoretically, if everything is perfect, you have the perfect model, you started out very close to the real solution, it might do that for a long time. But as soon as some noise, some external perturbation is going to give you. So what you do in practice is you combine those two things, to combine this feed-forward logic and the feedback logic. So here's an example. You would have a torque, that is multiplied with that modeled inertial moment. You put your desired trajectory just like before, but now you also put these error terms in here. This should again have the index E, it's an error term, like the PID term, and there you have that. And so that is doing both of those things, and that's a very good form of control. It's very, well, not how typical, but it's used often like that. It's so it's just the 3D version of what I just wrote down. It still amounts to controlling each joint. No, so sorry. Actually, this is the one where I'm not having the integral term, or actually I'm a bit confused because here's the desired and these are the error terms. I don't remember exactly what that is. Actually, this seems wrong. Yeah. So forget that. Maybe something's wrong here. So this is the more general form. So here you have the feed forward. So this is the thing where you insert the desired trajectory, and by having these other terms, by having the multiplying these terms, you use the model to anticipate, to make sure that you're close to the actual physical solution. And here you have your feedback terms. Yeah, that's the common form that is being used. I don't know. There must be some mistake on this one. That's the common form that's being used. Because if you think about that, then you effectively, for your error, you have that kind of equation if these model parts here are close enough to the real parts. Yeah, we don't have to go more into the details of that. Now, the So this is just like in the best, and so different approaches differ for exactly how they do that. You know, how do they use, what do they use here? In here, is it an estimate or is it a prediction? You might have a Kalman filter that combines your prediction and your estimate. So there's a lot of variance of how to do that optimally. So commercial robot arms will have control schemes like that, different variations, and are extraordinarily good. It's very difficult to beat that. Now, the one point where they don't work so well, so that's the kind of stuff when you see these robot arms in movies, right? Industrial robot arms now do very cool, very precise movement. They have very high repeatability, and they can reach very quickly, with all the interaction torques taking place, right? They are very heavy, and so they have to really generate just the right profile to put the fingertip to the right point. The one point where that breaks down is when they are physically interacting with an object, right? And now there is actual contact, so reaction forces. Now it depends on, so the interaction, if you have a rigid body and if it touches another rigid body, degree of freedom goes away. And if it's perfectly rigid, you get infinite torques or forces, right? It is only, now is a matter how elastic that object is, how much resistance it makes, right? So you get into a whole different domain. It's a singularity, not from a purely kinematic point of view, it's a singularity, because your arm cannot actually really move into the object, but it will move into the object because the object is deformable. It might be, depending on how rigid it is, might be a piece of steel, it can deform a little bit and so on. And so in reality, of course, you want it to deform in a certain way. Maybe you want to scrape something off, or you have some milling, right? With some machine that's supposed to just exert a certain amount of force. And that's very difficult. And still today, it's difficult to do that, right? So the state of the art is it's not really done with robot arms. They have more specialized machines for that, like milling machines and so on. And there's a whole research field that deals with that. This, how your robot interacts with the world, is sometimes called impedance. So it's a somewhat formal way of thinking about that. So for instance, if I think of this object as one I want to interact with, I might want to give this object, let's say this is the robot arm I'm interacting with, I want to give it a well-defined impedance. That is, I want the robot to resist me in a definable way. For instance, the robot approximates a damped mass spring arrangement, and I want to have it a particular elasticity constant, and a particular inertial constant, and a particular viscous, damping. So, for instance, if you are guiding a robot arm now and moving it around, you might want to have something like that, so that the forces the robot arm generates in reaction to you are within a definable range, and the rate of change of these forces, like the velocity terms, are of a certain kind, so that you can, as a human, can tolerate those. So there you're not designing just the robot, the kinematics of the robot or the kinetics of the robot arm to do a certain thing, but also this dynamics of some tool point, let's say the end effect of the robot. And so that's a very desirable thing. There's a lot of work on that. So originally, most of this work comes from teleoperation. So you're controlling a robot arm to do something somewhere else, and the human is controlling it. Remember, in these chemical chambers, for instance, where you're operating on something, and then in the chemical reaction chamber, I don't know, something is being poured, so on, and there you might even want to have feedback that you feel in your manipulator what the robot, if the robot arm encounters resistance, and then you want to have a well-defined model like that. So that's some form of human-robot interaction. And you could imagine that could even be like you had a robot arm on Mars, right? And want to remote control it on Mars. So that's a very active topic of research still. One aspect is that to give feedback to the human operator. It's complicated, but also to make that the arm has these impedance properties, like somewhat like a human, that so if it touches, that it doesn't ramp up the forces too much, but does something reasonable what you impose. And behind that is another piece of technology that was also developed by the same Khatib, whose name we encountered in potential field approach around the same time, a little bit later. And that's now standard. That's he's a very famous guy. Stanford. He's actually the main editor of the Handbook of Robotics that I pointed to earlier. So he did what is called the operation space formulation. It's actually, in a way, in hindsight, it's kind of a straightforward thing, but it was quite revolutionary at the time. And it took a long time for this to be usable because of the computation involved to do that in real time. So the idea is that your robot arm has this equation that it's just a little bit different notation, but the Q would be like your joint angles, right? That's what we just wrote down. That's the actual dynamics of your arm. And these would be the torques generated by your motors. But what you want is to know what the equation of motion of that is in hand space, the anti-vector space here called X. And so you want to write down an effective equation of motion for your hand. And there would be, and these would be the kind of forces that act on your hand to bring about the movement. And if you have that formulation, you could now understand, you could kind of now describe what kind of impedance your hand has in the world. And the relationship between those two can be figured out mathematically. You can actually write down these matrices here if you know those and vice versa. For instance, the forces and the torques are connected through this form. This is the transpose of the Jacobi, which you encountered earlier. Again, I don't explain that in detail, but that's one step that you have to do to bring in desired properties of the hand in space. There was actually, so someone called Hogan came up with a scheme of how to do compliant control, where you could really compute the torques you have to do to create a well-defined property at the end effector level. I have to transform that into joint space to know how to do that. Okay, so that's control. And you see that in this picture, control and planning are really nicely separate. You have the desired trajectory is computed from some algorithm, and the control just takes the desired trajectory. It doesn't have to know about the kinds of things that you were thinking about when you did the desired trajectory, right? These are really separate fields. And there is actually a certain mathematical characterization that says that under certain circumstances, you can just always separate planning from control. So it's really mathematically separate. Sometimes you might want to not separate that. And that is actually what Khatib did. So I'll just point that. So Khatib's original work was actually a little richer than what we talked about, because we just talked about in the vehicle case. So remember that in the potential field approach, he had this idea of having these gradients of some virtual forces, potential fields. The gradients would be virtual forces. And so his idea was to insert these forces into the operational space equation of the dynamics of the arm, and therefore it would be integrated with control. That is, you're not just computing purely abstract kinematic planning, but you're also taking into account what that means for the arm, the kind of interaction torques that arise and so on. And so all the physical terms would be exposed to the potential field. So the solution of that equation would be already your control signal. Right? So it goes much deeper than what we discussed. That was actually not realized so it's not just theory. It wasn't realized in most of the robot, and it took years until they created an interface where this could actually be done in real time, because it requires some kind of interface where you compute the torques from a somewhat complex dynamic equation in the operational space. Last thing I want to mention is the notion of optimal control. Some of you might have heard that. It's actually, strictly speaking, not really part of control per se. It's really more a form of planning in a way, but it takes into account properties of the plan. So the optimal control problem is defined as a problem of finding out a control signal, so something that you can actuate for a given plant. Plant is just a general term for whatever system you're having that has a certain well-defined dynamics. And you want to find the time course of that signal that brings about that change from some initial value to a desired final value at a desired time, given the plant's property. So it is a planning problem, but it takes into account control problems. So the most famous example is if you're, an algorithm, you have an automatic train, you replace the train driver, right? You might think that's trivial to do, train driver. It's just this little lever with a torque meter, with electrical motors, right? It's easier even than in a car. And so it drives into the station, and just has to, or the tram driver here of the metro, right? The U35. So it just has to stop at a certain point. Well, it actually interacts with control because you can imagine that if the metro is full of people, then it will take more counter current for braking than if it's less full. And still you have to reduce the speed to stand. But when you stand, you also want to stand at the right position, right? You want to stand at just the right position and with zero velocity from an initial velocity that might even vary and given different control, that is different inertial moments, for instance, of the vehicle, right? This is a complicated thing. So that's not just enough to send one particular signal at a particular time. It's a whole time course of lever motions, let's say, in the metro, well, so kind of signals you send down to the motors. And it's the time course of those signals that will achieve the final state. So it is a planning problem, but it's a planning problem that takes into account the control properties of your system. And so there is a theory about that. So in practice, what you do is you have some cost function that you can minimize. So usually there are multiple different time courses of U that can achieve that. You can start earlier and break more slowly, or later and breaks harder. You can imagine different profiles. And you make it so unique by saying I minimize and energy change or some variable like that. And then you can solve that problem. And it is, there are general equations for that, the famous Kalman inequality, but it's it's generally not easy to solve, and it's numerical in most of the cases. And we're doing actually using this kind of approach in our work at this institute. For instance, we're using this. We have a model of the arm and of the muscles also, and actually of some reflex loops in the muscle, which is a bit more complicated. We'll hear a little bit about that next week from Lei, but not in this mathematical detail. So we have a model of this, and we are observing the trajectories of the hand, and then we're trying to figure out what was the signal that the brain must have sent to the spinal cord, to those reflex loops. And we're doing this by saying, okay, that's the desired outcome. So what was the signal that came in? And we have succeeded in doing that in some cases, and looking at and properties of that signal. That's actually the frontier of research here. It's not, people measure stuff in the motor cortex, but there is no real relationship to that, right? And that's one of our goals, to bridge that gap between what we know about what is generated in the brain and what we know functionally must have arrived at the muscles to bring about that movement. The complication is the spinal cord actually has complicated neural circuits that can transform a signal in new ways to bring about the movement. So it's just this term optimal control that you use. Yeah, so that's our research agenda. So there's work going on here about topics like that.